I'd like to introduce today's speaker is Dr. Kahn, who up until just a week or two ago was he just retired in December. Congratulations. And he was a senior research scientist, climate and radiation lab. And of course, Ralph has a PhD in applied physics from Harvard. He spent 20 years at JPL in research on climate change on Earth and Mars. Then he came to Goddard as an aerosol scientist and led research on aerosols and climate change. He's also an adjunct professor at the University of Maryland. He chairs the Coast Guard Commission on Earth's Surface Meteorology and Climate. Got numerous awards, including best awards, including NASA Exceptional Service Medal, NASA Outstanding Leadership Medal, the Robert H. Goddard Award for Exceptional Achievement in Science, the AGU Kaufman Award, and the William Nordberg Memorial Award for Earth Science. He's also a fellow of the AGU, so very special opportunity to have Ralph with us. And he's going to speak to us on reducing the uncertainty in climate predictions, steps towards realizing the potential of NASA's Earth observation system, which he's been working through since it began, and reducing aerosol-related climate forcing uncertainty. So Ralph, let me know that he's about to move to Boulder, Colorado, to continue his work at the University of Colorado. So we're really fortunate to have him to speak to us today. Please welcome Dr. Ralph Kahn.
Thank you so much for the introduction. I will try and speak as quickly as possible through my slides, but I wanted to give you a full story here of this important topic, which is, of course, climate change and how we are able to predict the effects of decisions that we might make in terms of mitigation or adaptation. An important part of this is the role of airborne particles in the atmosphere, which includes desert dust, volcanic ash, wildfire smoke, pollution particles, sea salt. The symbol here in the middle is what I call the three-way street, and I will explain to you what that actually means as we go along. I'll point out now that the three components, the three elements there are the satellites in the upper left, the suborbital observations that we can make either from the surface or from aircraft in the upper right, and climate modeling, which is at the bottom of the slide. And I think I can advance the slide this way. Do that there. Okay, this doesn't show up especially well, but if you squint a little bit, you can see the light gray lines there. So what this is the global mean temperature values. The solid black line is the data record that we have for global mean surface temperature anomalies. So let's see, -1 degree, 0, and up. The set of lighter lines there are a collection of models that inform the IPCC reports. And in this case, the values are all normalized for 1995.
Ralph, could you hold the mic?
Okay. The models are normalized to 1995 to 2014, which is the period for which we have the best climate record of global surface temperature. And you see that the models all follow very nicely that curved line all the way up to about 2022, or however long this data goes. And then they diverge dramatically. And the global mean surface temperature can be anywhere from 0 to +2 in terms of the anomaly. Now this is an indication of how poorly the models can actually make predictions. The models are not entirely independent of the data record going from 1850 to the end of the climate record. But as soon as there's no longer a constraint, the models diverge dramatically. And that should give us a clue as to how important it will be to do a better job of constraining the models.
Can you hold the mic closer?
Okay. All
Right
right.
here.
Oh, I'm sorry. All right. Well, I think we got the point of this slide. I'll move forward. So, at the left, is the equation there is the simplest conceivable way of describing climate change. You have the forcing on the left, and you have the response, which could be the global mean surface temperature, for example, on the right. N is the ocean heat content, because that tends to be an extra sink for additional heat in the Earth system. F is the forcing, which includes the greenhouse gas forcing. It includes the reduction in forcing that would be caused by aerosols in the atmosphere, for example. And S is the climate sensitivity. So the way in which S is determined is you take the climate data record on the right of that equation, which I showed you in the previous slide, and you take your estimates for the forcing on the left, and you use that to solve the climate sensitivity. And the uncertainty in the climate sensitivity is the way in which the IPCC community judges their ability to make predictions. Now, on the right here is a chart from the IPCC 2013 report, and I just put that up there to mention that of all the uncertainties, and they've listed the greenhouse gases and so on, the primary uncertainties are associated with aerosols, and I've circled them in green. One of them is what we call the direct aerosol radiative forcing, which is the way in which particles in the atmosphere would cool the surface. They could conceivably warm the atmosphere. You have dark particles. And then the other bar there is for the effect that aerosols have on clouds, because in order to make a cloud droplet, under most circumstances, you need to have a particle to start with. And that's the role that aerosols play in aerosol cloud interactions. So here are the estimates of the climate sensitivity, starting with the China report in 1979, and going all the way up to the most recent IPCC report, which came out about a year and a half ago. And the point is that the uncertainty in the climate sensitivity, which is to say the uncertainty in our ability to make predictions, has not appreciably diminished for this entire record. Okay, so now I think I've established the need for us to do a better job of constraining the climate sensitivity. So I'm going to talk a little bit about aerosols, because that's what I study, and again, that's the primary term in the uncertainties. So these are now ground-based views of some aerosol sources. In the upper left there is a dust storm in Phoenix. In the upper right, a wildfire. This one was in Oregon. And at the bottom there is a volcanic eruption. That one was the one from about 2 years ago at Tonga in the South Pacific. And these are views of the same kinds of phenomena from space. So there's a dust storm in the upper left. This is coming off the Sahara Desert and going into the North Atlantic. Wildfire in Alaska. There are actually a number of wildfires here. You can see the plume. I guess the quality of the projection isn't perfect, but it's a nice sharp image actually originally. And there are little red dots which we use from MODIS data to get the location of the hot spots using infrared sounding at 4 microns. And then a GOES image from the Tonga eruption right there. It was a very dramatic eruption. Okay, so the very first observation of aerosols from space that was published is in a paper by Joe Prospero, looking at a dust storm coming off of North Africa. This was now acquired in 1967, and the paper came out in 1970, and they tracked the dust storm across the Atlantic Ocean with the ESA-5 satellite, the Vidicon camera. You can see the fiducials in the image there, and the arrow I have pointing to the dust storm itself. Satellites have provided the understanding and actually the inspiration for an appreciation of the fact that aerosols are so important in understanding climate change and the global mean surface temperature in particular. And these images showing that aerosols can have transcontinental transports, can be substantial in terms of their optical depth and the impact they're likely to have on the radiation balance, both directly and indirectly through clouds. So this is the role that satellites play. Now, I'll say a little bit more, and again, not everything is showing up here, I'm afraid, on the title there. But okay, so the role that aerosols play in climate, there's surface cooling by reflecting sunlight, there's atmospheric warming when there are dark particles that can absorb sunlight like black carbon. There's cloud brightening because, again, clouds are required to serve as cloud condensation nuclei and ice nuclei in order to make clouds under most circumstances. The effects that they can have include increasing the cloud lifetime, causing cloud dissipation, invigorating clouds, which is a mechanism that I can explain if there's a lot of interest. Other things that aerosols do in the Earth system include possibility of ocean fertilization in places where the ocean is iron poor. Desert dust that has available iron, and there's another whole story about that, can end up fertilizing the ocean and creating biology, fertilizing land. There's a story about phosphorus in the Amazon that might come from Sahara dust, transport of pollen, disease vectors, and effects on the atmospheric circulation due to the radiative effects of aerosols. Now, in addition, climate change affects aerosols. So aerosols can affect climate in the ways I described in the previous slide. Although you can't see the titles here, I'm sorry about that. The effects that climate can have on aerosols, including desertification, deforestation, drying of land, water resources like Owens Dry Lake, for example, or the Aral Sea, overgrazing, farming practices of various types, like deep plowing, for example. Changing wind and precipitation patterns can increase the amount of dust aerosol in the atmosphere. Changing temperature and humidity conditions and disease vectors that can affect vegetation and trees as a result often create increases, and this is well documented now in the recent past, increasing wildfires. So then you get wildfire smoke that way. So climate effects, oops, I don't know what just happened.
Now they're trying to get the red. This is the video.
Okay. So, oh, there we go. Now you can actually see the slides that I was showing earlier. I'm not going to go back, I'm just going to go forward. So, okay, so how do we make progress given the importance of the aerosols, given the uncertainty that persists in our uncertainty in climate sensitivity? So each one of these three elements, the satellites, the suborbital elements, and the models, each one has a unique and essential role to play in reducing the uncertainty in climate sensitivity. And the three-way street are actually the colored arrows and the associated text that goes with it. And I will go through some examples of how we're contributing to each of those arrows and how we need to contribute in the future. I will just mention that the three-way street paper appeared in Reviews of Geophysics in July of this past year, and my co-authors are listed there. A number of my colleagues from Goddard and from NOAA and from universities all participated in putting this together. Both, well, there were modelers and there were measurement folks, representatives of all three of the elements in this figure. So I'm going to start with EOS. This is, I'm talking about the contributions we've been able to make to the aerosol science from satellites. That's the first part of this. This is the Terra satellite. It was launched on December the 18th of 1999, and it took first light in February of 2000. Our instrument was MISR, which is down there, and MODIS up here. I've been the aerosol scientist for MISR since before launch. There are three other instruments that all are interesting and important, but I won't talk about them today. But MISR and MODIS are the two that I will draw on because because those are the ones that have contributed the most to our understanding of aerosols. And there's a launch there. All of us from NASA enjoy seeing launches, so I included a picture of the launch. And I mentioned that we have almost 24 years of data from MISR and MODIS at this point from the Terra satellite. The Terra satellite is about the size and weight of a full-grown Indian elephant. And I mentioned that, thank you, I appreciate that. I mentioned that in the press conference when they launched the Terra satellite. Unfortunately, the lead scientist for EOS at the time didn't think I was taking it seriously enough, but the press enjoyed the analogy, and it's, yes, it's about the size and weight of a full-grown Indian. So the MODIS instrument here, it was the next generation of an instrument called AVHR that many of you no doubt are familiar with. A broad swath, multispectral imager, single view, and the particulars are all here. There are bands going all the way from the UV into the infrared, thermal infrared, and MODIS has many, many constituencies studying land surface. I showed the fire image earlier. The 4-micron channel is used to identify hotspots for wildfires from space. Improvements over AVHR include the calibration of the instrument, which is really quite exceptional, the spatial resolution, and the spectral region number of bands, which are an improvement over AVHR considerably. The kind of thing we can get about aerosols from MODIS include what we call the aerosol optical depth, which is a measure of the column amount of aerosol. There are not many constraints on aerosol type from MODIS, but you can get a loose constraint on the size. You can tell whether the particles are coarse mode dominated or fine mode dominated, where the dividing line is about a micron in size. Coarse mode would include things particles that are created mechanically, like desert dust and sea salt. The fine mode includes pollution, includes secondary aerosols, includes smoke, a lot of particles except ash from volcanoes. And at the bottom here, I just mentioned that recently we figured out ways of actually making estimates of the uncertainty in the optical depth, to estimate the uncertainty for each measurement. So rather than just doing it statistically, we're actually being able to do it on a pixel level. Pixel levels for MODIS are 1 kilometer. So we get a global picture once every day or two at that level of resolution with that kind of information, aerosol amounts, column amounts. Now, MISR is our instrument, and again, to carry the analogies to an absurd level, MISR is about the size of a steamer trunk, and it weighs about 350 pounds. I made that analogy too, and at the time, unfortunately, the most popular movie was something called the Titanic. And so I got in trouble for that too. Nevertheless, it's about the size of a steamer trunk. It has 9 cameras that are pointed in 9 directions along the line of sight, along the path, the orbit path. It's in an orbital path that crosses very close to the poles. And each of the 9 cameras are canted at different angles, so we get 9 angular views. And each one has 4 line arrays, blue, green, red, and a near infrared channel at 866. So with those 4 channels and those 9 cameras, we get 36 strips, approximately 340 kilometers wide. It takes about a week for MISR to get the entire planet. So unlike MODIS, we don't catch absolutely everything, but we have once a week global observations at 9 angles and 4 wavelengths, which gives us a lot of information on particle properties. So one of the things we can do is we can use the parallax from the multi-angle views in order to get the height. So if a feature is very near the surface, the background will not appear to move very much when you look from one angle or a different angle. So there's the camera in different angles. Whereas if the plume is high in the atmosphere, then the background will shift significantly relative to the feature as you look from different angles. So this now is an example from the Williams Flats Fire Complex plume, and this is our map from MISR of the plume heights, and you can see that it's all around 2.5 kilometers. There were 2 plumes actually in this field of view. And this one is the north plume, and this one is the south plume. There's the south plume there and the north plume there. And these are the profile maps, and you can see the particles move downwind from the source. The green is the surface terrain. And okay, so the other thing is, because we have 9 cameras, it takes 7 minutes for all 9 cameras to be a given location on the surface. That gives us enough time to see the motion, the proper motion of features in the plume. And so we can make a motion correction. So we actually get the wind vectors, so we can see. So we can do 2 things with that. One of them is we can correct the parallax for the actual motion. So that's what the blue dots are as opposed to the red dots, which are uncorrected. The other thing we can do is we can estimate the time horizons, because we have a time scale based on the motion vectors and a distance from the imagery. Okay. So we take this data, and we've done a number of things with this. Maria Valmartin, who worked as a postdoc in my group from about 2009 to 2014 or so. And we did a climatology of North America over a number of years using different biomes. And you can see the different years here and the different biomes, shrublands, grasslands, and forests. We learned a lot about different ecosystems and how smoke is produced in those different ecosystems. I had another postdoc who actually she worked with me as a graduate student as well. She did her PhD with me at Purdue University, Maria Petrenko. And so we had the idea of estimating the smoke source strength, which is another thing. So in order to constrain sources in climate models, so this is again our effort to try and improve our climate modeling, there are 2 things that are used to characterize an aerosol source. One of them is the source strength, the amount of smoke or dust or whatever it is coming out of the source, and the injection height. So the injection height is the plume height that we can do with MISR. And the source strength we try to constrain in the following way. We have a snapshot of optical depth from Lotus, and I showed you that earlier. And then we can take a climate model and run it in the forward direction with different source strengths. And we sample the climate model at the time of the observation. And when we have an optical depth that matches, we then have the source strength. And that turned out to work quite well in certain locations, in places where the plumes from the source, from the wildfires, were relatively isolated, that there was not a lot of background aerosol to confuse the process. And in places where the fire source was sufficiently substantial so that it wasn't in the noise of the optical depth. So wherever we had substantial plumes, we were able to do this and get both the source strength constraint and the injection height. So this is how we constrain models. We built a climatology. I'm not going to go into details about this, but we had 23,000 cases, had a whole bunch of students at JPL, at University of Maryland, and Sheffield, which is where Maria Valmartin ended up, and we digitized all those plumes. We had to build a climatology. And among the things we could do is we could map out where on the planet smoke was ejected above the planetary boundary layer. Now, the planetary boundary layer is the lowest few kilometers of the atmosphere. It varies with season and latitude, but it's about a couple of kilometers typically. And if smoke is ejected above the boundary layer, then the smoke will stay aloft longer, it can travel farther, and it can have a bigger climate impact. So that turns out to be important. We used 2 different definitions of the boundary layer height. One was to use the narrow-tube reanalysis model, and so these are the colors showing the percentage of plumes that were injected above the boundary layer in 2 seasons, the summer and the winter in the northern hemisphere. And then we also used an arbitrary 2 kilometers because narrative is not 100% reliable. So this is the kind of thing you can do, which again helps us constrain the behavior of aerosols in climate models. Talking about plume heights, I'd be remiss if I didn't at least mention Calypso, which was our space-based LiDAR that operated for 17 years. Its mission terminated. It was originally scheduled for just a few years of operation. It lasted 17. And it died last summer. But we were able to get very nice constraints on aerosol and cloud vertical distributions. The Calypso LiDAR is a bit more sensitive than the MISR parallax, but MISR does pretty well. We get a vertical resolution of between 250 and 500 meters. Calypso 70 meters. So, but Calypso just has a pencil width of sensitivity, so it's 100 meter swath width. So you don't get the whole Earth, you only get 233 specific orbits, but you can aggregate them, and my colleague Kahn put together this aggregation of the seasonal behavior of the vertical distribution of dust and other aerosols off of East China for different seasons. So you can see how we hit that constraint. Now with the multi-angle data from MISR, we can also get information about particle properties, and that turns out to be important too. This angle is the scattering angle. There's the sun, there's the camera, that's the scattering. The horizontal axis in these three plots is this angle theta, and the vertical axis is a relative scale. And what I've done here, these were from some of our pre-launch sensitivity studies. We changed, theoretically, we just simulated different particle sizes, different particle shapes, and different particle light absorption, so dark and light particles, big and small particles, spherical and non-spherical particles. And we sample this in 9 places, and what you can see is that these curves vary considerably when you vary the size, the shape, and the light absorption. And so that's how we get information on particle properties. So here's an example. This was the Los Alamos fire in New Mexico. There's Los Alamos right there in these 3 images. I processed these 3 images identically. These are 3 MISR images. This is the nadir view, straight down, and this is the 60-degree forward and aft view. And you can see, first of all, this is brown and these are whiter. That's significant because here you're looking through a rather short path through the atmosphere. Here you're looking through double the path through the atmosphere. And so you're seeing more atmosphere, which is why these images are whiter. You also see that you can barely see the plume in this image. You can see it very clearly in these images. Again, this gives us information of the aerosol amounts. It's quantitative information. We know the angles very precisely. You also see that these are bluish, and they're different. These are different scattering angles that we're looking at. And so, again, that's information of the particle size and the particle light absorption. So these were smoke particles. They were small, medium particles, and they were somewhat light absorbing. And one last thing I want to show, if you can just see it there, there's this little whitish wisp here, and it's up there in this image. So this is the parallax. This is near the surface, so it doesn't move appreciably from these images. The parallax here, because this is a high up cirrus kind of cloud, it moves a lot, so that's how we get the plume heights. Okay, so another example here, a smoke plume off the Yucatan Peninsula, the optical depth, the aerosol amount, you can see this is the amount, angstrom exponent, which is inversely proportional to the particle size. These are small, medium particles. And the optical depth fraction spherical from our retrievals. These are spherical, small spherical particles. This is now dust off the Sahara Desert. Optical depth. These are now large particles, and they're non-spherical, so you can see the difference. We did this globally. Barbara Gately worked with me in my group at JPL for a number of years, and we were able to map out the particle types globally. There are a whole lot of stories about this. If you're interested, our paper explains the multi-level classification that we used here. The reason for doing this is because the sensitivity to optical depth is very good up to very low optical depths, but the sensitivity to particle properties, the size, the shape, and the light absorption, that diminishes as the amount of aerosol in the colony optical depth goes down. And so these multi-tiered things allow us to make distinctions when we have less information, and then make finer distinctions when we have more information. So I've now circled these couple of arrows in our three-way street diagram. This is now how satellites can help models. And I've already kind of illustrated some of that with the source strength and the injection height and the particle type information. I will also mention that here contribution that satellites can make to making in situ observations. And so here are some examples. So this is again the Williams flat spy. Remember I showed you the plume heights that we retrieved. Now these are the particle properties that we retrieved. There's the optical depth, there's the angstrom exponent, and there's the brightness, the single scattering of the particles. Dark particles near the smoke source. Brighter particles here, and very bright particles downwind. So these are now three regimes. Remember I told you we can get the age horizons from the motion vectors and the distance. So this is about half an hour. This is a little over 2 hours, and this is 200 minutes here. This is the north plume, that was the south plume. If you look down here at the particles, you see the particles get bigger up here in region 2. So what's happening here is we're also getting brighter particles. This is now the formation of brown smoke. So there's black smoke near the smoke source, and then we get brown smoke about an hour after the smoke is emitted. And then we get a mixture of, because the optical depth goes way down, a mixture of background particles, so you get very bright particles down there. The south plume is just pretty much black smoke the whole way through. So that one didn't change very much, whereas this one had that nice evolution that we were able to see. There was a field campaign that we participated in called FireXAQ that took aircraft data of this plume at the time. So here's the interpretation, the black smoke and the brown smoke, and these two charts you saw. So we were able to validate our observations, our interpretations as well, from aircraft measurements that were made contemporaneously during the FireX campaign that we participated in. So taking that a number of steps further, Katie Noyes, who did her PhD with me as well, we then looked at 663 plumes in Canada and Alaska and aggregated the kind of data that I showed you in the previous slides for this many plumes. And we're able to put statistically together the changes in particle size and the changes in particle type, or light absorption. And we're able to do that for different ecosystems, forest ecosystems, grassy ecosystems, and what we call woody, which is kind of in between the two. And you can see that the time scales for transitions, and even the types of transitions in particle size and particle type, vary with ecosystem type. And again, these are the kinds of constraints that belong in models. And I can go into, we have some papers about this. We can go into a lot of detail about it. The point is that we're getting these constraints that can be used to constrain the climate models to improve our ability. Now volcanoes, we also looked at volcanoes, and I had a postdoc working with me for a number of years. She's now at the University of Stirling in Scotland as a permanent faculty member now, and we're still working together on volcanoes. What a lot of people who aren't into geology aren't aware is that at any one time there are at least a dozen volcanoes going off somewhere on the planet. And so what we have here is a chart of some of the volcanoes that have gone off since about 1960. The ones that have star asterisks on them are the ones that are possible to produce mega eruptions, which is to say they have the geologic characteristics that would allow for a mega eruption. The ones that are circled in red are monitored somewhat, and the ones that are circled in yellow are monitored rather well suborbitally. All the others are hardly monitored at all suborbitally. So this gives a role for the satellites to play in providing information about volcanic eruptions. So one of the things that Verity and I did was we looked at a number of different volcanoes over Kamchatka, in Iceland, and this one is Halahorin from Iceland. And these cartoons here tell us the particle types that we were able to deduce. And the Halahorin eruption produced a lot of sulfate. So these green and yellow are sulfate particles of different sizes. The brown and gray are what we infer as ash particles based on the particle size and shape, because ash particles will be bigger and non-spherical. The plume heights are indicated here in these black and gray bars, and you can see the activity there. The amount of SO2, which is a precursor to the sulfate that's in these plumes, That we monitor with the OMI UV observations. So those little X's are the SO2 that was emitted. And then down here are the thermal anomalies measured from MODIS. And so what you see in this case is that the volcanic eruption started rather dramatically here in August of 2014, and by February of 2015 it had systematically diminished. So again, a lot of stories here, we have papers about this, but the idea is we can characterize that volcanic eruption this way from space. Okay, this is now from a paper I'm just, it's actually in review right now in JGR. For the Tonga eruption, this was the observations that we had of the plume from that eruption going west from Tonga across all the way through the Indian Ocean. The plume heights, validation from the Calypso LiDAR, validation of particle properties from ground-based measurements at the Aerosol station up here in Western Australia. Particle properties, these particles are fine mode particles. Their optical depth is about 0.6 or so when they get to Western Australia. They're all spherical and non-light absorbing. So we're able to characterize them. And so we did this for 8 observations, starting from the volcano and going west, all the way up to almost to Madagascar. And we found something very interesting that again turns out to be important for constraining models. Using the plume heights, we found in these green dots, there was a layer of aerosol from this eruption that was near the tropopause, so about 12 to 18 kilometers. Those are the green dots. And those particles were small, medium, and they didn't change appreciably much in size as they evolved. The blue dots were for a layer that existed in the mid-stratosphere at about 30 kilometers. And there, the particles actually started off as quite small and grew with time over the period of a week. Now, this eruption, I showed you a picture at the beginning, put a lot of water vapor into the stratosphere. That was its big effect. It was a sub-ocean eruption, and it put this enormous amount of water into the stratosphere. And models predicted that what would happen is that that would create sulfate particles that would form rapidly and grow in size. And we actually were able to measure that quantitatively. And so again, another constraint we can place on the models. Okay, so now we'll come back to our three-way street. And I think, yeah, so now I'll talk about how models can help with the observations. Okay, so one of the things that models can do is they can help us fill gaps. So there are cloudy places like Brazilian rainforests. There are topographically complex places like the Himalayas. There are places where there's snow and ice or where it's polar night. Those are places where our aerosol observations from space are limited or unavailable. Models can help us fill that in using physics and source-receptor relationships. The other thing models can do is in places where the optical depth is low, they can provide us with additional information about particle properties. Because the models don't really care about the optical depth. They just have a source, they know what the particle properties are there, they can calculate how they evolve with time, and then they can tell you what they estimate the particle properties to be at the receptor place where the satellite observations were made. So we did this for North America using the go-kart model. My colleague Leanne Shin, who runs the go-kart model, worked with me on this, and we had a student, Shin Lee, who did a lot of the analysis and plotting of the work. And we figured out the kinds of constraints. It turns out the angstrom exponent, that spectral dependence of optical depth, and the absorbing optical depth were the two variables that we were able to use as constraints on the retrieval algorithms based on the models, and we got a better result by adjusting the MISR results to take into account the go-kart model. Okay, so models are required for making predictions, but they're also useful in making predictions to determine where you fly your aircraft if you're going to make aircraft measurements. So that's another thing. They can provide, after the fact, an estimate of what we were looking at from satellites or from suborbital measurements. So those are all the things on the three-way street where the models can contribute to measurements. So one last thing, let me talk about the suborbital measurements. And this is the area in which the most new work needs to be done. So I had a paper in BAMS, in the Bulletin of the American Meteorological Society in 2017 with 17 or 18 of my colleagues. As a satellite person, I participated in more than a dozen field campaigns with aircraft, and I developed a healthy respect for the guys that make the measurements from the aircraft. And I realized that to get the detailed microphysical properties of particles, you need to have in situ measurements. Although we can get loose constraints on size, shape, and light absorption from space, we cannot get light absorption at the level of detail that you need it in order to constrain climate forcing from satellites alone. And there are a number of other things which come up in the next slide, but I'll just say quickly that because for a given source in a given season, the particle properties tend to be repeatable, even if the amounts vary enormously. So some years there might be a lot of biomass burning in Alaska, other years there might be very little, but it's the same vegetation burning in the same ecosystem. The particle properties tend to be the same. So you don't have to measure it with the aircraft all the time, you just have to measure it really well once. Okay, so these are some of the things that you can only measure from in situ. You can measure the hydrophobicity, which is to say how much the particles change in their properties when the relative humidity changes. And that's important to understand to interpret the optical depth, because the optical depth is measured under ambient conditions from space. It's also required in order to do a proper job of modeling aerosol cloud interactions. So hydrophobicity is one. The mass extinction efficiency is an extremely important variable because the models, whether it's climate models or air quality models, they all bookkeep something called the aerosol mass, whereas we measure the optical extinction. So there's a variable called the mass extinction efficiency, which relates the optical depth, the aerosol extinction, to the aerosol mass. Any attempt for taking satellite observations and using them to constrain a model requires assuming the mass extinction efficiency. Well, if you remember from that very early slide I showed where the models are all over the place after the period of observations that constrained all the models, one of the reasons for that is that the mass extinction efficiency is assumed to be all different values by different model communities. There's no constraint on it. So this has to be measured in situ. The light absorption properties need to be measured better, and the CCN properties need to be measured better. And again, because unlike aerosol microphysical properties tend to be repeatable from year to year for a given source in a given season, this is feasible to do, and it needs to be done. So that pretty much concludes my survey here. This is my group. We contribute, by no means the only ones in the community who do this, but I have a number of members of my group. We have a research algorithm that allows us to do the detailed particle properties from MISR. It's the best available set of particle properties from the Earth observing system to date. We also have MINX, which is our tool that gives us the layer heights and the motion vectors. We get aerosol type, aerosol amount. We study wildfires, we study aerosol cloud interactions. There's a whole set of stories about that. Dr. Lawrence Zamora, who's a research associate in my group, is leading that effort. There's the SAMCAM, those in situ measurements, there are volcano studies, climate and air quality. And those are my group members. They're all over the world right now, but they're all doing good work. And I'll end with that slide about the three-way street. And I'll thank you. That was my time.
Questions?
Ernie.
Yeah, the idea of putting aerosols into the stratosphere is mitigating factor, which affects global warming. What do you think of the idea of putting an aerosol layer into the stratosphere to mitigate global warming? And the second part of that question is, we know enough about aerosols, they are conductive, if there isn't instruments.
Well, you basically just gave my answer. Okay, so the question for anybody who didn't hear was, there's something called geoengineering, and one of the leading geoengineering ideas is to have aircraft inject sulfate into the stratosphere to make particles to presumably cool the Earth's surface. And the motivation for that had come from the idea that when you have a major volcanic eruption that does in fact inject sulfate into the stratosphere, you do make sulfate particles, and once you've made sulfate particles, there is a net cooling of the Earth as a whole. I actually testified to the National Academy panel on geoengineering on this in 2013, and the bottom line is, it's a terrible idea. And so let me explain why. I know some of my well-intentioned, I mean, there are two groups of people that are advocating for this. One are well-intentioned people who don't fully understand how little we know about the stratosphere and how many negative consequences could result from this. And the other group are more nefarious, and they just want to have an escape hatch so that they can say, well, we can continue burning fossil fuels and doing all the other things that we're doing because we have this. Okay, so some of the things that can go wrong. First of all, the volcanic eruptions tend to be short-lived events. Doing this would have to be done on a continuing basis. If you would ever stop, especially if this was an excuse for not mitigating the other causes of climate change, you would get a dramatic and very rapid increase in global temperature as soon as it stopped. You'd also be producing a perpetual rain of acid particles into the polar regions. And what that will do is aside from the fact that it could contribute to changing the environment in the Arctic and in the Antarctic, it might contribute to reducing the ice content and so on, which could add. There were things called tropopause folds that we don't understand a great deal about. But in the interface between the stratosphere and the troposphere, that tropopause layer sometimes folds over. And it is possible that the particles we inject into the stratosphere could end up getting put into the troposphere, into the upper troposphere, and nucleate cirrus. Now, cirrus in the upper troposphere will warm the surface. So it could actually have the opposite effect, if that turned out to be important. And then one more thing, and there are other things too, but one more, which is this would mitigate the global mean surface temperature, which is a very convenient number if you want one number to talk about climate change. However, the habitability of the planet depends not only on the global mean surface temperature, but also on things like the temperature differences between land and ocean. The monsoons that provide water for 2/3 or so of the Earth's population depend on the oceans being cooler and the land being warmer in the summer. If you were to put a layer there permanently, you would diminish the land to ocean temperature difference. So you would diminish the monsoons. And there are some data points about that. Historically, the Nile River flow diminished after a major volcanic eruption some 1,500 years ago. There's geologic evidence for that. So, anyway, in short, it's a terrible idea. In spite of the fact that some very well-intentioned people are advocating for it. Okay.
So, Terra with Modus and MISR in its twilight.
Yes.
What or how will those observations be replaced?
All right.
It's a loaded question.
It is a loaded question, and you also know the answer. So, unfortunately, unfortunately, it's a very sad story. And again, this is something where those of us, and I include myself now, that have retired from NASA and are no longer in the civil service can possibly help with, which is lobbying. The AOS, which is the supposed follow-on to EOS, is unlikely to launch until 2030 at the earliest. The LiDAR that would be the replacement for Calypso that we lost last summer has already been de-scoped to a large extent and will be, at best, no better than Calypso, possibly not as good. There is no replacement for MISR at all. What there is an instrument called HARP that was an add-on instrument to the PACE mission, which is supposed to launch in the next month or so, which has some advantages, but also some significant disadvantages, including poor spatial resolution. Now, why that's important is because all the plumes that I showed you, whether they're volcanic plumes or wildfire plumes or dust plumes, which I didn't show you today, they require having spatial resolution on the order of 1 kilometer or better in order to actually resolve the features of the plume, which is what you need in order to get plume heights, injection heights, particle properties, horizon, all that sort of stuff. We're not going to get that for the foreseeable future. And right now, when it's discussed, everybody says, well, there's going to be Earth care from ESA, and that's going to do it, or the Chinese are going to do it, or something like that. I know that NASA responds well to competition from China or the Soviet Union at one time, and that's where we're going back to the moon now, because China's might beat us there. But in any case, this is a serious thing, and the importance of doing a better job of constraining the climate model so that we can do a better job of predicting what will happen based on different scenarios, understanding what certain mitigation strategies are likely to yield in terms of improvements of habitability in the future. This all requires getting this data, including SAMCAM, including the aircraft program that doesn't exist. So these are the things that need to be done. And to the extent that we choose to take it seriously before more disasters take place, these are things we need to do. They're eminently doable, I'll say that. We have all the
Taylor survey say about it. In 2017.
Okay. I'm no longer an NASA employee, so I can speak freely. The decadal survey, they selected people and they instructed them not to be too controversial. So there was a certain mitigating factor on the directness with which the decadal survey was written. So there were other problems with the decadal survey, the way it was structured. One of them was that they asked the decadal survey to make budget estimates. And they were in no position to do so. The numbers that they gave were impossibly low. I'll give you one example from my own experience. I was on the committee for suborbital measurements for AOS, for the follow-on to EOS. And the ostensible charge to that committee was to identify work that could not be done from space that needed to be done suborbitally to supplement it, like SAMCAM, for example. That was the reason I was on that committee. The budget was capped at $30 million. The instruments on AOS, as best we knew at the time, were all expecting their calibration of level 1 products and the validation of level 2 products to be done by this suborbital budget. Modus alone would have used up the whole $30 million. So just level 1 calibration, just one instrument, the whole budget. So what the committee ended up doing was recommending a couple of field campaigns that would last a few weeks and do a few interesting things. No doubt they'd be good field campaigns, but they don't address the charge to the committee. What I did after 2 years of serving on that committee with increasing frustration was I stopped going to the weekly telecons and wrote the three-way street paper instead. So that's what I did. I think that answers the question.
Follow on to your discussion about the systems. Are any other countries picking up the slack in any way?
Possibly. It's a little hard to tell. For example, I know that Italy has offered to provide several instruments for AOS. What the quality of those instruments will be is something that we don't have any reading on. How well they'll interface with our system, whether they follow the same engineering practices that we do for quality assurance and so on. It's relatively unconstrained because we're not paying for it. So it's possible. ESA has a program that's possible that will, hopefully EarthCare will eventually launch. It was supposed to launch 5 or 6 years ago and it keeps getting postponed. So that could help. We have a very capable scientific community here in Europe and Asia. But without data, the community is going to dissipate. And then the expertise will be lost, and that's another issue. China may be producing things. They ostensibly had an HSRL, high spectral resolution LiDAR, which would have been the next generation LiDAR, that was launched sometime last year. But nobody's seen any data from it. So we have no idea what it is doing, whether it's working and they're just not sharing, or whether it's not working, we don't know. We don't know. So, I mean, NASA has been the preeminent agency for making observations from space, which is why I did 38 years at NASA myself. And we have the expertise, both on the engineering and on the science side. And NASA should be doing this. And the only thing I can say is that we need to make that case wherever we can, especially if we're concerned about climate change, which we all are, especially those of us that have kids and grandkids.
I have a question.
Yeah?
Since most of the elements that is affecting aerosol, what is the effects of the bombs that are being dropped from these two wars that are happening? How severe are their effects?
On a global scale, they're negligible. On a regional scale, they could be considerable. I haven't looked at that, so I don't know that specifically. But the kinds of things we're talking about, the natural phenomena, as well as the aggregate of pollution from vehicles and so on, is much greater. It's just much greater in scale. But regionally, those things can be very important. And I just haven't looked at that.
The other one, sir, is that I have some friends that are also physicists and PhDs, and they were challenging the chains of these battery-operated cars. That when batteries are dead, where are they going to dispose of?
So this is a big question. I don't know if everybody heard it. It has to do, the question specifically was about the life cycle of batteries in electric cars and how environmentally damaging that can question is, any of these mitigation strategies, one has to look at the whole life cycle. So, for example, biofuels. The idea that you burn corn, that you use corn to produce alcohol, and if you actually add up all the fuel that you need to use in order to make the fertilizer and to plow the fields and so on, you end up using more fuel than you would have if you would just burn the fuel to begin with. So the life cycle has to be viewed carefully. There are a lot of smart people, chemists, physicists, systems engineers, that if they're given the right charge, which is to say, to think about the life cycle, to think creatively about all the aspects, there are things we can do that will mitigate the effects of whatever choices we make. But the work has to be done, and it has to be commissioned as such. And if it's not, then absolutely, there'll be surprises of all sorts.
I'm going to